Okay, so we go now to deflection in beams, and I think in this topic there will be two methods of solving the deflection of your beam. So most likely in this topic, this one is an important topic since this might be carried into the next subject, because there you will be designing some mga beams, mga let's say mga girders, and the deflection of your elements or structural elements will be of importance sa inyong design process. So, nana siya yung mga restrictions sa deflections, so on and so forth. So here is we're going to have the introduction to beam deflections. So we're going to get the formula for your deflection, which is going to be the Bernoulli-Euler Beam Equation. And for the first part, I think I'm going to try to skim a bit faster on these slides, because this is more of a derivation type of um, section. So I leave this one to you. So probably in the next few slides that I'm going to present, you're going to be presented with different um, differential equations. So since kika na mo sa DE, di ba, from Sir Fornis, so probably you'll be able to understand the derivation that is going to happen in this topic. And also the first two methods, especially the first method, so we have the direct integration method, and I am pretty confident since you are coming from my class, di ba, sa integral calculus. So probably the integration part is just an easy aspect in this type of method. And then we have the area moment method also as well. So area moment theorem and area moment method are the same. Okay, so probably what I can say between the two methods is that it's the same as the shear and moment equations, wherein the first one is you need to formulate an equation, and this one is similar to the direct integration method, which is you are going to have an equation which represents the entire span of the beam. Then for the shortcut, this is more likely the area moment method, which is a shorter version of the itong mga equations ninyo. Okay, so I think we can now start with the derivation part first. Okay, so for example, this is your beam, and let's say you have an applied load in your beam. So you have a concentrated, so varying concentrated load. So it's not a uniformly distributed load. So you also have a concentrated load P. Okay, so let's say this is the deflection of your beam according to what the beam has experienced with the given types of loading. Now, our concern here is we're going to, di ba sa mga derivation process sa ato ang mga formulas, let's say for example, for the area in our integral calculus, but we're going to use a particular kind of strip, or let's say a representative area or representative section. So that's what we're going to do now. So we're going to get a representative strip, which is in this format here. Okay, so kanang naka-shaded area. Okay, so this is our differential x since we are in the x-axis, di ba? Sorry. Okay, and that particular distance, the deflection going towards the x-axis is y distance. That would be our deflection. Okay, so usually the deflection in terms of sa beam ninyo is y, but in other cases, so pili siya katong delta gani nga smaller case. So okay, and this distance towards the deflection point is x. Okay, so this next part is probably now the complicated part. So you have now different elements in your strip. So kani siya, it's zoomed out lang siya. So this particular strip in with accordance to the elastic curve. Okay. So you have your d theta here. You have your dx. You have your ds. So ds is probably I think that would be the length of the arc. Diba sa ato ang formula sa integral calculus. So we consider our arc length as ds. Diba? So ds or s is equal to katong square root of 1 plus dy over dx squared, diba? So ito siya. Okay, so rho would be the radius of this sector. But again, since para di mo maglibog sa derivation, so try to read the book. But I think in the book of katong Python and Cuselas, so it doesn't mention about the derivation aspect of the Bernoulli-Euler equation, but it went directly to the topic of double integration. Okay. So if you create tangent lines, so you can create also the d theta equivalent. Okay, so from calculus, so we can say that the change of your y and your x can be related to the tangent function. But that's why we have tangent theta is equal to dy over dx. But for very small angles, so you can just opt out tangent because it will necessarily be equal to its angle itself because it's very small. So diya sa inyo figure, it just muna siya dako lang siya because i-zoom out man siya, di ba? But if you are taking a representative strip or representative sector, usually the angle is very small, which means that even though that we use a certain type of trigo function, the difference won't really matter. So muna siyang ang keynote here. So differentiating the previous equation, so we now get the second derivative. So d theta over dx is now equal to dy squared over dx squared. Second derivative of x with respect to, second derivative of y with respect to x. And that would be the first equation. So again, probably this might be a bit confusing because we are bombarded with mathematical equations, but try to understand as we go along with discussion. Okay, I for myself before, katong college student pa ko, bilis ako kasabot sa derivation aspect as well, but makasabot ako once I study it on my own. Okay, so considering the length of the differential strip or differential arc length, so that would be rho times d theta, di ba? I think for, sa inyong solid geometry, di ba, ang inyong sector can be defined by r theta, di ba? But since we are now considering it as a differential length, so differential arc length, So it is ds. That's why it has a d. Then our theta as well is also a differential theta because it is coming from the strip as well. So it is changing, di ba? Muna siya mag-change um, sa inyong elastic curve. Now for the radius, so anywhere on the arc length, so the radius would be the same. That's why it is not a differential radius. So only the arc length and the theta. Okay, so since the elastic curve is relatively flat, so di ba katong sa ato ang arc length topic sa calculus 2. So most likely the arc length can be expressed as a straight line because it's a very small distance, di ba? Kanang gamay ra kay siya nga part sa inyong whole arc length. So mo to siya tong gibuhat sa calculus 2 wherein the ds or the hypotenuse is a straight line instead of a curved line, and that's what we use to how to derive the formula for arc length sa calculus na to. So dire is the same, but our ds is not equal to the hypotenuse, but it's equal to the dx. Okay, it's in the x-axis man, diba? And it's relatively flat because it's a very small unit of the whole elastic curve. Okay, so rearranging the terms, we get 1 over rho is equal to d theta over ds. And again, it is approximately equal to d theta is equal to dx. So kaniya tong equal lang ani. Okay, so substituting to the first equation, diba katong d theta over dx is equal to second derivative of y with respect to x. So we now have 1 over rho is equal to the second derivative of y with respect to x. Okay, so you can also validate your equation using the differential equation for radius of curvature. So I think you are pretty familiar with this equation. So try to look this one online or try to look in your notes before. So radius of curvature. So I think you have this topic in your differential equations. Okay, so when dy over dx is equal to 0, or most likely approximately equal to 0, the equation can be simplified to the format earlier, the second equation presented in the previous slide. But it's the second equation in the previous slide. Now this would be the madugo part. Oh, sorry. Okay, so after we have determined the radius, 1 over rho is equal to the second derivative of y with respect to x. Now from this figure, we can now establish a certain geometry of the triangle. So we now have tangent d theta all over 2. So we're going to create a triangle, diba? So that we can relate some stuff in the diagram. So it is equal to the d delta over 2 all over the half of d delta over y, and d delta is equal to 2y tangent d theta over 2. So where is this coming from? So this is coming from this triangle here in B, an section of your strain diagram. So I think the strain diagram can be established with the previous topics we have discussed, but since I was not able to discuss to you how to create the strain diagram, so I think establishing the strain diagram is similar to the shear and moment diagram, but pa doon lang kakilid. And I think this is also a second topic sa inyong shear and moment equations wherein you're going to have the shear in beams. I didn't actually discuss because we're running out of time. That's why I jumped into the beam deflections. Okay. Okay, so naghanap equations no? So medyo madugo na dyan kayo siya. And I'm not going to try to force nga makasabot mo sa derivation because again, grabe siya kalisod yun sabto ng derivation kay daghan siya og mga constraints na i-consider. Then you have to use some differential equations and you have to set your own boundary conditions for you to be able to understand the derivation aspect of the Bernoulli-Euler equation. So sige lang, I'm going to post this. I'm going to post all the slides that we have discussed so far so that you won't be able to para maka-review sad mo sa inyong concept. So aside from that, I also forgot to give you the assignment for the shear and moment there. Or nakatag ba ko or wala? So I really forgot kay medyo na busy jud lately. Okay, so in short, sa B and C section, so muna pakilid ang iyahang strain and stress diagram. So it's because when you have this beam, diba, in the x-axis, then you try to cut this section here. Ang iyahang gi-consider na element sa iyahang strain and stress is in the x direction. That's why ni-create siya og stress and strain inaana siya, di ba? Along with the width of the beam. So later on, when you go to your higher subjects sa yung reinforced concrete, you'll be experiencing the same kind of diagrams sa inyong strain and stress na diagram. So for example, this is your reinforced beam. Or cross section lang sa reinforced beam ninyo. Yeah, on the right side, so dihan mo mag-create sa inyong stress diagram ana. Depending on the type of loading that you're going to be given. Okay, so this will be the different elements of your section. So derivation of the flexure equation. So as you can see, you have different formulas presented in the, the screen. So as you can see in equation number 6, it is just a ratio and proportion between the different elements of the stress diagram. So the stress, the total, the certain stress of your representative strip all over Y, then the whole span, the total stress all over the total, or the center span, diba? That's C. Okay, and then we're going to use the bending moment for us to be able to derive, diba? So the moment is equal to the sum of the moments about the neutral axis. So moment is equal to the summation of the different moments, diba? On each span, kung pila ka bok moments ang iyang makuha. And with this, we're going to get a certain integral since we are going to have it from negative C going to C. So lower limit is negative C, which is on the bottom part of this stress diagram going towards C. which is at the topmost part of your equation. So of course, y would be representing the different parts of your stress diagram. So not only restricted to this portion, but you can also um, it can also be represented in the other aspect as well. So mura siya kanang vertical strip, di ba? So katong ato ang discussion before sa ato ang integral calculus. So you can change the location of your representative section or strip. Diba? So pwede siya magbalin-balin as long as it is representing the entire bounded region. So in this case, it's the entire stress diagram. Okay, so with that, if upon integrating your equation, we now have our total stress, which is equal to mc over I. So muna siya ang atong, so after all the discussion that we have made sa mga libog na discussion, so all you have to memorize is this formula. Sigma sub c is equal to mc over I, wherein c is the distance from the top of the beam going to the center point of the beam. So it's just like h over 2 lang siya, but it's represented as c. So mc over I. So I is the moment of inertia, and most likely the moment of inertia is already a given formula. So it's a fixed formula, and I think it's found in your book. So if I'm not mistaken, it might be found on the appendix part. Okay, that's what I remember sa among calculus book before. I mean sa among materials book before, katong bipital gyapon. But it's at the back portion. But sa karon, I have not yet fully scanned chapter, I think it's chapter 5 or 6 sa book. Basta so far ako makita is kanipang mga formula. Okay, so m is also the moment. So since kibamata mo solve for the moment, so I think what's left for us to determine is kaning moment of inertia, kaning I. All right, so you can also have it as my over I, but most likely in books and in references, it's really mc over I. Okay. So unfortunately, wala ko yung mga shortcut na mga way of memorizing the formulas. So pwede po nyo butang MCU, di ba? MCU over I. Ano, pwede sad. Para dali siya memorize. MCU under I. Ano, di ba? MCU I. Yeah, showing na ba yung Dr. Strange, no? Okay, so I'm sorry. So integrating further, deriving further our equations from equation 5, you can now use equation 7 for us to be able to use that particular equation to input it in equation 5. So d theta is equal to d theta over dx. So derivative of theta with respect to x is equal to m, the moment, all over ei. So modulus of elasticity and moment of inertia. So usually these two are fixed components. So that's why you can just try to ignore this part later on once we go to the solving aspect. And then we're just going to plug that one later once we are done with the integration aspect, since the first method will be the double integration method. Okay. Okay, so we now have the final format. Since d theta is equal to dy over dx, so this becomes the double derivative or the second derivative of y with respect to x is equal to m over ei. So what we're going to remember is this formula also, because this is what we're going to use once we go to the double integration aspect. So muna siya yung button, di ba? So what you need to remember is the equation on the last slide, which is mc over I. And then the other formula would be this one, equation number 9. Second derivative of y over dx squared is equal to m over ei. So moment, modulus of elasticity, and the moment of inertia. So I think with this particular topic, all you have to do is to get the moment first, and then we're going to proceed with the double integration aspect. So I think that's the difficult part lang siguro kay after integrating the said equation, what's next to do is kato ng pag-set sa boundary conditions wherein you have to be very observant on, or let's say you have to be very accurate on setting your boundary conditions for your equations to be correct, because you need to set your equations na dapat ang kanang equation mo represent sa entire span sa inyong beam. Okay, so I think the critical point or the critical area in the first method would be to set the boundary conditions. So katong integration aspect, medyo dali ra kay to siya because since we already know how to integrate our equations. Okay, so let's now go to the direct integration method. So in other books, we put siya double integration because you'll be integrating twice. Diba? Okay, since you are presented with katong equation 9, since it's in the second derivative, so para mawala ang inyong second derivative, you need to integrate twice. Okay, para makaabot siya sa iyang neutral zone. Okay? So again, in other books, it's called double integration method. In some books, it's also direct integration method. Basta, same concept na inyong makita gyapon. So probably I'll be discussing one technique now, and then later and then on Tuesday I'm going to discuss the second method. Kay mas taas siya og kanang kuan ng katong area moment, because since magsige tag drawing ng diagram, kani it's purely mathematical, it's purely computational, kay puro siya mga equations. Okay, so let's go to the first kuan. So again, from the discussion that we have made earlier, so the rotation and deflection at any point of the beam can be measured by integrating the Bernoulli-Euler equation. So again, the Bernoulli-Euler equation is kato ato ang gi-derive ganina. Katong t second derivative of y with respect to x is equal to m over ei. So muna siya ang gibot ang kuan, diba? Integrating the Bernoulli-Euler equation. So meaning we have to integrate this one. So that's why it's the integral of m over ei with respect to x. So it's always with respect to x because all of our beams is in the x direction. So if it's in the y direction, so column na siya, diba? It's not a beam anymore. And when you're going to evaluate columns, it's also a different kind of solution compared to beams. Kay ang inyong column ang good is compression ang iyang loading, di ba? Yung bending kay napud sa kilid ang burot. So nasa x direction po ang iyang bending. Okay? So, di ba, with all the stuff that we have done, we have gone through with the derivation, what we're going to do is just integrate this part of the section. Okay? So, mura na siya inyong button for this method. So again, the advantage of this method is that the equation that you're going to get is it's going to represent the entire strip of the beam. So katong second method, which I'm going to discuss later or next week. So medyo kuan siya. shortcut siya, nya dili po siya accurate in a sense na dili siya sige kag solve again and again because dili siya ma-represent ang dili siya maka-represent sa entire strip, only at a given location. Okay, so again, since it's a second derivative, we're going to have it as a double integration, diba? And it gives you the y component because since you are integrating twice, so may mo siyang dy and then the dy becomes y, diba? And that will be the distance going to your point of the, the distance going to the point of the deflection. So the boundary conditions usually at supports are used to solve the constants of integration. So again, this is a critical part in the calculation aspect because so even though we're going to get the boundary conditions at the supports, so I think you need to know how to understand, or let's say how to clearly see, or let's say analyze what boundary conditions are found at the supports. So later on, ato na siya makitaan once we go to the example. Okay, so let's discuss the first problem para di mo maglibog unsaon siya pag solve. So first thing is, since you are given with only variables here, W and then L, then R1 and then R2. Okay, so first of all is we're going to solve the reactions R1 and R2. So even though we don't have any values for your load and your length, so we can still get the particular moment by, the reactions by getting the moments at, let's say, R2 at first. Diba? Moment at R2 is equal to 0. So let's say this one is counterclockwise positive. So what you're going to have would be W times L excuse, times L over 2, and then minus R1 times L, diba? Is equal to 0. So what you're going to have would be WL squared over 2 is equal to R times L. So ako na siyang transpose on the right side para puro siya positive directly. So R1 would be equal to WL all over 2. So most likely R2 would also be the same since the given span is symmetrical. So this one is also equal to R2. Okay, so the next part would be getting now the moment equation, since it's a key formula for the method. Ba? So how are we going to get the moment, or let's say the general moment equation of the beam? So para makuha siya, ang atong button is we're going to take moments at a certain location. So kung tag magkatungkuan katong, let's say, katong equation method sa inyong shear and moment equation. So ang atong button is we're going to, let's say, cut a section here. So let's say this one is X distance. Well, let's say that one is X distance. And of course, the center of this cut section would be X over 2, di ba? Kani siya half distance. Let's try to change color para kita ninyo. Okay, so let's say this is the cut section of your so di ba mo na itong ibuhat sa ato ang atong normal method of obtaining the shear and moment equation, di ba? Atong equation method and the other one is shortcut. So mura siyang equation method wherein you're going to get a certain part of the beam, so section. So in this case, so since the load is uniform all throughout, wala na other loading, wala na concentrated load, so we can just set one moment equation here, diba? So pwede ra siya isakabok. So again, this would be our x distance, and then half along the way would be this would be x over 2. So this one would be x, and then half of it would be x over 2. So getting the general moment, so all you have to do is take moments on the left part of the equation. So let's say summation moments on the left part. So it's equal to, so again, the span would be from the moment A to B. Okay, so how do you determine this one? Is that you're going to get WL over 2x. So again, taking the moment, di ba, about going to the left, di ba? So kasi maglibog mo sa ang left part. So not at R1, but if let's say this is the cut section, you take moments here, kani siya. Dire ka mo take moments. Mamana siya going towards the left. Okay, so let's say our sign convention would be the opposite. So positive clockwise, ha? So again, it won't matter kung asa pa dong inyong kon as long as you properly designate your sign convention. So di na siya ma-matter jud. Okay, so taking moments on the left part of the cut section, so you're going to have R1 times X and then minus W times X over 2. So now R1 is WL over 2. WL over 2 times X minus WX squared over 2. And then this would be our moment. So W so 1/2 WLX minus 1/2 WX squared. Okay. And this particular moment that we have solved, this will be solved in the double integration method or the direct integration method. So this will be our moment sa katong equation presented earlier. So kato ganing kon double integral katong m over ei. Okay, so this would be the solution for the reactions, and then this would be the solution for the moment. So diba, you cut a section here, same as the shear and moment equations, establishing the shear and moment equations, the same method. You cut a certain section and then you try to analyze that particular section. So you take moments about the cut section for you to be able to determine the moment. Okay, so again, this moment here that we have solved, this will be going towards the the equation earlier, itong Bernoulli-Euler Beam Equation. Okay, so for the next part, so marag wala na ko na siya makuha ng slides. So let me try to empty lang sa okay. So again, since you're going to use the Bernoulli-Euler equation, so that will be second derivative of y with respect to x squared, then m over ei. So again, coming from the last slide, our m is 1/2 WLX minus 1/2 WX squared, and then over EI. Again, since constant itong EI, so we can just multiply EI on the other side first, or you may just try to put EI here na 1 over EI, then you're going to get the double integration of M, the moment. So of course, if double integration on the left side, on the right side, you have to also double integrate the left side. But ato lang siyang i-properly show ang solution na para kuhan siya. Now, first thing that you need to do, since we're going to integrate twice, so this is going to be d squared y dx squared. So integrating on the left side, integrating on the right side, that would be the first type of, the first integration na atong ibuhat. So this would give us the first equation wherein ato siyang integrate una, di ba? So the second derivative of y becomes the dy na lang, di ba? First derivative. Okay, so from second derivative, this is now dy over dx. Okay, and then let's say 1 over ei, since this one is a constant, then multiplied by 1/2. So take note that w and l are constant. What is changing here is just the x value, diba? Since we are integrating to x, so meaning wala siyang partial derivative wherein every other variable is held constant, and ang atong integrate is katurang inyong variable of interest, which is in this case the variable x. So 1/2 times 1/2, diba? 1/2 w x squared over 2. But that would be for the first one. So we only integrated x variable here. Then 1/2 w x cubed over 3. Then don't forget plus c, di ba? So plus c pataw na. Natay plus c sa ating equation. Or you may include c in all together in the okay. So this would be the first integration. So next we integrate again. Now this time our dy over dx is now y. Y equals 1 over ei. Before that, ato sa simplify ba para kita mo lisod. So this will give us dy over dx and then 1 over EI. Then this is going to be 1/4 WLX squared minus 1/6 WX cubed plus C. Okay. So now we integrate again. And this time we're going to get Y now. Y is equal to 1 over EI. So 1/4 WLX cubed over 3 minus 1/6 WX to the power of 4 over 4. Then integrating C, diba? We now have X, diba? CX, yeah, plus C pa dyan, another variable nga constant. So para di mo maglibog, so just put C1X here, then the other constant would be 2. Okay, the two constants cannot be combined because the other constant has now a variable X together with it, diba? So muna ato siyang gilabel as C1X, then the other one is C2. Okay, then simplifying the equation, we now have 1 over EI and then 1/4 WX cubed. So 1 over 12 WX cubed minus 1 over 24 WX to the power of 4 plus C1X plus C2. Okay, and then that would be our value of the deflection, Y. So this equation here will represent the entire elastic curve sa ato ang beam shown above, but we cannot solve it yet because we still have a constant C1 and C2. So, di ba, coming from your differential equations, you can set boundaries for you to be able to determine C1 and C2. So, in our case, we're going to determine those boundary conditions at the supports. Okay, mas dali makuha og boundary conditions at the support compared with the other parts of the beam. Okay, di ba? If other parts of beam, so meaning nana mo Y aspects sa inyong kuan, di ba? Sa support, okay, mas dali sa support because ang atong Y value, atong deflection is 0, di ba? Kay wala man deflection sa support compared sa kuan. Okay, so setting the boundary conditions. So let me so setting the boundary conditions. So let me write again the equation. 1 over EI, then 1 over, sige to, 1 over 12, 1 over 24. Okay, so 1 over 12 WX cubed minus 1 over 24 WX to the power 4, and then plus C1X plus C2. Okay, so setting the boundary conditions. So boundary conditions. So again, the purpose of setting our boundary conditions would be to be able to solve the two constants, C1 and C2. Okay, so let's say at X is equal to 0, the deflection at X is equal to 0, meaning at point A, Y is equal to 0 as well, diba? So meaning you're going to get 0 is equal to 1 over EI, diba? 1 over 12 WL times 0 cubed minus 1 over 24 W0 to the power 4 plus C1 times 0 plus C2. So meaning with all the given conditions, but 0 out, 0 out, 0 out. On the left side, it's also 0. So what's left is just C2. So C2 is equal to 0. So it's C2 over EI, but if you multiply EI to the other side, C2 is equal to 0 gyapon. Diba? Now the other boundary conditions, sorry. So the other boundary condition would be at the full span, diba? At the other point of the support, which is at point P. So when X is equal to L, so diba, the entire span going from A to B, that is X equals L. So at full span, the deflection is still 0, diba? Okay, there's no deflection at point B because it is being supported. So again, going back to the given equation above, so 0 is equal to 1 over EI. Then you're going to have it as 1 over 12 WL times L cube minus 1 over 24 W times L to the power 4 times C times L, and then plus 0 coming from the second boundary, coming from the first or the previous line. So C2 is now 0. So ito lang i-bracket para. Okay, so what you're going to have now is you're going to have 1 over EI. Then you're going to have 1 over 12 WL to the power of 4 minus 1 over 24 WL to the power of 4 plus C1 times L. So isolating C1, then divide everything by EI. Okay, since wala tayo space. So the answer would be negative 1 over 24. So C1 is equal to negative 1 over 24 WL cube okay. So of course, nawala ang EI because ma-divide ka po siya tanan, di ba? Ma-cancel out ka po ng EI. So C1 is equal to negative 1 over 24 L cube. And then once you have your C1 and C2, so you're going to complete now your kaninyong deflection equation, which represents the entire span of the beam. Sorry kaya kayo, marago kayo ng tubig. Okay, so this would be now the solution to the second part. Double integration pa itong ibuhat ha. Wala pa tayong mahuman. Okay. So medyo shortcut lang siya dire, but the answer is the same. Excuse. Okay, so the next part would be to determine the slope equation, bakatong theta, and also the deflection equation. So since we now have the deflection equation coming from B, I think all you have to do is to determine now the katong ang deflection atong slope equation. Okay, murag na siya ma-create sa slope, diba? Slope sa ato ang beam deflection. Okay, so so this is the final answer. So for the slope equation, it's just the first integral first integration sa inyong Bernoulli-Euler, di ba? Ang deflection equation is the second integration sa inyong Bernoulli-Euler. So, katong kanina ang atong ibuhat, katong dy squared over dx squared, then dy over dx, then lastly would be the y, di ba? So, kani siya is referring to the slope equation. So, muna, mas importante dyan na ato siyang i-show sa solution. This portion here is representing the deflection equation. First integral, this one is second integral. So if we go back to the point of the slide we're in, katong nag-solve ta og first and second derivative, I mean first and second integral, ang atong slope equation sa first integral is just C1, di ba? So katong C1 na atong answer is muna siya, di ba? Incorporated in the answer. Okay. So later on, this is important because you'll be getting the slopes from points A and B. So again, this is the equations presented will be used later on for you to be able to determine the slope of the equation, slope sa inyong deflection curve, and also get the particular locations, or let's say the deflection on each points throughout the entire span of the beam. Muna siyang letter B, deflection equation. All right? Okay, so usually in a symmetrical type of beam, kanang dili siya uniformly distributed. I mean, kanang wala siya other loads except the uniformly distributed load, or let's say it's symmetrical but the loads are concentrated. Usually the maximum point of the deflection is at the midspan if it's symmetrical. So again, if it's symmetrical, the max deflection is at midspan. So may na siya sa L over 2 ang inyong. So since symmetrical siya, so you can also try to determine the behavior of the deflection. So meaning symmetrical po siya, di ba? So ana siya. And this one would be the maximum deflection. If it's symmetrical, if dili siya symmetrical, so probably there's another problem that you need to encounter. I mean that you're going to encounter. And I think you're capable of establishing the moment equation since kibaw na mga to sa area shear and moment equation, di ba? So usually we use the slope equation to determine the rotation at support A, di ba? That's why it's theta. So rotation meaning the deflection of the beam. Saan man siya pa-explain na? Ang iyahang rotation downward, di ba? In the y-axis, that's why it's theta. With respect to x-axis there, padung siya ubos. So muna siyang rotation. That's why you're going to solve the rotation at A and then B as well. So again, this is coming from the first integral. So try to go back to the recording later kung ginsa ni siya pagkuha ni siya, di ba? Basta we have solved this one earlier in the previous slide. Okay? So of course, when you're going to solve for the rotation at support A, so all I have to do is to set a boundary condition because at A, x is equal to 0, di ba? So muna siya. So you're going to have it here. Okay? Then of course, the rotation is clockwise, di ba? Okay, padung siya sa sulod man, di ba? A and then B as well. So this is for B support. So when B is at full span, di ba? So A is 0, P is total full L. X is equal to L Joule. Again, the slope equation is giving you the direction of the deflection of the beam. Diba? So that's why it's also important to take note of the arrows at okay. So for the maximum deflection, so maximum deflection occurs at L over 2 because again, since this one is symmetrical. But for cases wherein it's not symmetrical, so you're going to solve it using itong manually jud, like at every span you're going to let X be equal to a certain value of span jud sa inyong beam. Okay, for example, your diagram is not symmetrical, so dapat at X is equal to 1, X is equal to 2, so yun siyang ka ng kuan sa tagsa og solve ang inyong deflection. Okay, so Y max is equal to this answer, and it's downward. Obviously, it's downward because your loads are going down sa, diba? So meaning it is deflecting downwards. So again, we rarely see cases wherein our loads are upward. So probably upward siya if it's a counteracting support, diba? Meaning your support is not a static support, but it's a driving support sad. Nag-push po ang support against your structure. So again, we rarely see those cases wherein our loads are going upward. So usually loads are going upward if it's static, or let's say it's only a reaction. Okay. So to sum it up all, again, what we did here was just to get the moment first. That's the first step. The second step would be to get the second derivative. Diba? Kaning equation. So set up the equation next. So M over EI. First there is reactions and then moment. Di na to mag-reaction na kay marag basic tam kind of reaction. So pwede ra moment directly because it's already a given that you need to solve for the support. So third step would be to determine the first integral. This would be our, again, this would be equal to the slope equation. Then the second integral would be y is equal to the double integral of the given expression. And again, this is our deflection equation. So sa kadaghan to discuss ganina no sa katong derivation. Dali di kay siya i-solve dai. So 1, 2, 3, and 4 steps. You have only 4 steps for you to be able to determine the slope of your deflection curve or your elastic curve, and also solve for the different magnitudes of your deflection at any given point. So I think muna siya ang power sa inyong slope equation and deflection equation. Okay, at any given point, you can solve the certain magnitude of your slope and deflection at that particular distance. So it's the same as the shear and moment equation, diba? At any given point, whether magbutang mong decimal point ya sa inyong distance, you can solve a particular magnitude of slope and deflection sa inyong given span. All right, so questions or clarifications?
Not so far, sir.
So I'm going to discuss next meeting the area moment method. So probably I'll post today the assignment sa inyong shear and moment, but at least ma-practice mo gamay. And then I'm also going to try to look for assignments regarding the double integration or the direct integration rather, and and also the area moment. So probably if I'm willing out, so try answering this problem. So this one is not symmetrical anymore, but again, the process would be, I think this one is very tedious because you're going to create, let's say, pila ka box pa na? Pila ka box section. So you're going to create one section here, wherein it represents the uniformly distributed load. And you also have to express it here, wherein it also involves the reaction. And you also have to get the moment on the right side. So kani siya left side and right side. Okay, you have to take note also sa inyong concentrated load. Okay, so muna siya inyong tanawon. So kani take moments about the left, so meaning take moments here. Kani siya take moments here towards the left and also towards the right to include the moment on the right side. So I'm going to show you the solution okay, para at least wa mi gamit ang solution no kaya ako man gyapon ni hatag din yung slide so gamit eh. So I'm just going to show you na siguro para at least for those of you who don't want to keep on alt tabbing going towards the PDF file. So okay, so